All right, we are starting chapter 8, which is on rational expressions and rational functions. So what we cover in chapter 8 is simplifying rational expressions as well as adding and subtracting rational expressions and then solving rational equations. So 8.1 is just simplifying rational expressions. We'll see some multiplication and division in this section as well. So first of all, a rational expression is a ratio of two polynomial expressions. So something like this, or if you just look at your note sheet, any of the examples, those are all rational expressions. And when you're simplifying these, you're simplifying a fraction. So the way you simplify a fraction when you just have numbers is the same concept. However, it's challenging or just looks maybe a little bit different when you have polynomials versus just numbers in the numerator and denominator. So I have here, just as with reducing fractions where you have numbers, when you simplify a rational expression, you're dividing the numerator and denominator by their greatest common factor. That part is important, that you are simplifying by canceling out factors and not canceling out terms. So if you notice, if you have the fraction 8 over 12, you might not write it out this way as 8 is 2 times 4, 12 is 3 times 4. You might just look at the 8 and 12 and say, oh, I could divide those both by 4, and that would give me 2 over 3. But you are canceling out a common factor. Factors are numbers or quantities that are being multiplied. So when I look at this expression, what I don't want you to do, I've referenced this a little bit already in previous chapters, is you cannot cancel the x squareds. These are terms because they are being added or subtracted to other quantities. They are not factors. Factors are being multiplied. So you cannot cancel these x squareds out, just like you can't cancel these x's out. What you have to do is factor these trinomials. So we go back to what we reviewed in chapter 4, factoring, and that would be factoring using the diamond. So we'll review that. X squared minus 4x plus 3 factors to x minus 3 and x minus 1, and then the bottom polynomial factors to x minus 5 times x minus 1. These quantities are being multiplied, and notice they both have a factor of x minus 1, so that those can get canceled, and then your answer or your simplified fraction is x minus 3 over x minus 5. And again, these x's cannot cancel because they are terms. So make sure you are only canceling factors, and when necessary, you need to factor either the numerator or denominator, or maybe both. So if I look at the examples under example 1, it says simplify each expression. Under what conditions is the expression undefined? So I'm going to look at that part second. So to simplify this, what I first want to look at is there any factoring I can do either in the numerator or the denominator? So I noticed for this one that the numerator is already factored, but the denominator, I have this trinomial that I can factor using the diamond. So I'd be multiplying to -6 and adding to -1, which the two numbers that work are 2 and -3. So I'm going to keep the numerator as it is, 4y times y minus 3 times y plus 4. And then in the denominator, I still have that y in front. And now because this is a 1y squared, I can go straight to my factors of y plus 2 times y minus 3. And once everything is factored, then I can cancel out any common factors. So I notice that on both the top and bottom, everything is being multiplied by just this y. I have a y on the top and the bottom. Those would be common factors. Those would cancel out. I also notice that both the top and bottom have a quantity y minus 3, so those can cancel out. And that's all they have in common, so my simplified expression is 4 times y plus 4 in the numerator, and then y plus 2 in the denominator. And again, that's as much as I can simplify. There are no other common factors, and I would leave it like this, so I don't have to distribute the 4. You can leave that factored out. Then, where it's undefined, This is actually what we talked about in the previous chapter, chapter 6, that whenever you have a quotient or a fraction, your denominator cannot be 0. And it's important that you are going back to the original denominator. So I could either look here, or I can actually look here where I had already factored it. So I know that this whole denominator, so y times y plus 2 times y minus 3, cannot equal 0. So then, just as when you factor and set it equal to 0, I would set each of these factors not equal to 0. So that means y itself cannot be 0, y plus 2 cannot be 0, y minus 3 cannot be 0. And so that gives me y can't be 0. This equation would give me y cannot be negative 2. This equation gives me y cannot equal positive 3. So these are three values that y cannot be because they make the original expression undefined. The denominator is 0. So I would include that after my simplified expression. I would say this is the simplified expression as long as y does not equal 0, comma, negative 2, comma, or 3. And that altogether would be the full answer to this question. Okay, so I have a couple other examples. So if we look at example B, same idea, but just to give you extra practice with it. So again, determine if you can factor anything in the numerator or denominator. Numerator is already factored. Denominator, I see I have y squared minus 9. So this, it's not a trinomial, so I'm not using the diamond, but this is a difference of perfect squares. So remember that this factors into y plus 3 times y minus 3. So you take the square root of the y squared, which is y, the square root of 9 is 3, 1's plus, 1's minus. That's how every difference of squares factors. So I have 3y times y plus 7 on the top over y plus 7 times y plus 3 times y minus 3 on the bottom. And I look for any common factors. I see that the top and bottom both have a y plus 7 that would cancel out, and that is it. So I am left with 3y over y plus 3 times y minus 3. That would be the simplified expression. Then I have to include again where it's undefined. So I go back to the original, or I'm actually going to go here where I already have it factored. So y plus 7, y plus 3, y minus 3 cannot be 0. That means if I set each of these not equal to 0, so y plus 7 can't be 0, y plus 3 can't be 0, y minus 3 can't be 0, which means y cannot be negative 7, y cannot be negative 3, and y cannot be positive 3. So my simplified expression such that y cannot equal negative 7, negative 3, or positive 3. All right, this next one, just as one additional practice, actually what I'm going to do is I'm going to work through it, not under the camera. Why don't you go ahead and try this one and then check your answer with mine and see that you got it correct. Okay, I'm going to show the response. If you need more time to try that on your own, feel free to pause it. But here would be the answer. So I noticed in the numerator, you can factor this trinomial using the diamond. So that becomes z plus 4 times z minus 2. The z minus 2's cancel, the z plus 5's cancel. So this would be the simplified expression. The denominator can't be 0, so z cannot be positive 1, negative 5, or positive 2. Okay, moving on then to a different set of examples. What's different about these ones is that there may be times where you have to factor out just the number -1 in order to get a common factor or for quantities to match. It can't always happen, but there's times where it can. So I'll show you how that works. So again, I start these the same way. Notice these directions just say simplify. It doesn't say to determine where it's undefined. So you don't have to do that second part of setting the denominator equal to 0 unless it asks. It doesn't ask for these ones probably because there's multiple variables, but you only have to give that if the problem asks for it. So I'm going to determine on the top and the bottom if I can factor. And I notice on the top, I don't have a trinomial, I don't have a difference of squares, but both terms have a z, so I have a GCF. So you're reviewing a lot of the different ways to factor in this chapter. So I can factor out a z on the top and have then the quantity x minus 4 with that z in front over. On the bottom, that's already factored, z squared times 4 minus x. Okay, so I get this. Now, if I have a z to the first power on the top and a z to the second power on the bottom, that means there's one z on top and 2 on the bottom, so that 1 on the top is going to cancel with only one of them from the bottom. So this is going to become a z just to the first power on the bottom. And then x minus 4 and 4 minus x, they are not the same thing, so they cannot just cancel each other out. But if you notice that you have the same terms in terms of the x and the 4, and all they are is it's just switched around. So it has to be subtraction if it's just switched like this. What that means is you can factor out a -1 from one of them to make them the same. So what I mean by that is if I take this and I factor out a -1, meaning I divide these both by -1, 4 divided by -1 is -4, and negative x divided by -1 is a positive x. And now if I switch this around, so I still have the -1 in front, this would be a positive x and a -4, so it's x minus 4, and now it does match the factor on the top. So now that I've done that, I can cancel them out, but I have this negative then in the denominator. So my simplified expression, since everything canceled on the top, everything canceled and there's just a 1 left. So make sure you're not bringing what's in the denominator up to the top. I still have a 1 on the top, and in the denominator I have a z multiplied with a -1, so I have a negative z. So it's 1 over negative z, or I could write that as just the negative in front of the whole fraction, or you could put the negative on the top with the 1. That doesn't matter, but -1 over z is the most simplified expression for that. So factoring out a -1 when you can. So if we look at B, here's just another example of that, example B. So again, looking at the top, looking for a GCF, I notice that both of these terms have an A and a B. So if I factor out an AB, I'm left with still a B from this term, and then -5 over, my denominator's already factored, 5 plus B times 5 minus B. And it looks like right now nothing cancels out. But again, this is where my attention is drawn because both of these are subtraction, they're just flipped around. So again, when that happens, you can factor out a -1 just from one of them. So say I do it with this one. I take out a -1. That gives me a -5 plus b. which if I switch that around, it's b minus 5. And then it does cancel on the top, but my denominator is now negative. So I would have AB on the top over a negative 1 times the quantity 5 plus B. You can certainly leave it like this. Again, you can put the negative in front of the fraction like I did here. You could put the negative on top with the AB, as long as you have that negative somewhere in your fraction to show that the fraction is negative. Okay, then the remaining examples, and we actually do more of this tomorrow, is multiplying and dividing. So think of how you multiply and divide fractions. When you multiply two fractions, you multiply the numerators and multiply the denominators. So that still applies even with our rational expressions when you have variables. And then to divide two fractions, you multiply by the multiplicative inverse, which is the reciprocal of the divisor. So there's two examples here with numbers that you're more familiar with. So when I multiply fractions, again, you might not actually write out all these steps in terms of factoring the numbers. What you'd probably do is either multiply the 2 by 15 to get 30, and then the 9 times 4 to get 36, and then you'd simplify 30 over 36. You can divide them both by 6 to get 5 over 6. Or, remember, you can also cross simplify. So I notice on this diagonal, I can divide both 2 and 4 by 2, which would make the 2 a 1 and the 4 a 2. I can also cross simplify the 9 and 15 and divide them both by 3. So the 15 divided by 3 is 5, 9 divided by 3 is 3. And then if I multiply across, I get 5 over 6 right away. So you either multiply and then you simplify, or you can simplify and then multiply. But either way, you should have the most simplified fraction in the end. Division is if I have a fraction divided by a fraction, remember, that's the same as changing the division to a multiplication problem. But if I divide by a fraction, that means I'm multiplying by its reciprocal. So if I'm dividing by 6 over 35, I flip that, and I'm now multiplying by 35 over 6. And now that it's a multiplication problem, I do exactly what I did over here. So we are going to apply this to rational expressions. So this is for your, your reference when you look back at your notes to help you out, but I'm just going to show you with some examples, and I think we might just go through a couple of these, not all of them. So for A, here you have to pay attention if it is multiplication or division. So it's multiplication. What I normally do is I'll look at just the coefficients. So the 6, the 21, the 15, the 18, and I'll cross-simplify the coefficients if I can. You can cross-simplify variables, but I tend to not do that, although it's not wrong if you do. Just be careful with how you do it. So if I look at 6 and 18, I know I can divide those both by 6. So this 6 would be a 1, the 18 would be 3. And then 15 and 21, I can both divide by 3. So the 21 becomes a 7 and the 15 becomes a 5. And then I'm going to multiply across. So I multiply the 1 and 7, which is 7. And then notice none of my variables on the top are the same. So I would just write them all, and it doesn't matter which order. I tend to write them in alphabetical order. So I would write the a cubed first and then the x, y. But if you put x, y, a cubed, that's still fine. And then on the bottom, 5 times 3 is 15. And again, none of my variables are the same. So just writing them all, I'll put them in order. So a, b squared, x to the 4th, y. And then you just have to make sure that this fraction for your coefficient is fully simplified. So this is now a problem like we had in chapter 5. So you're simplifying this using properties of exponents. So 7 over 15 is already simplified. But because I have an a cubed on the top with an a to the 1st on the bottom, that means I have 3 a's on top and 1 on the bottom. So that a on the bottom is going to cancel, and I'm going to have 2 left on the top. So I subtract their exponents. And then I still have the b on the bottom. That's the only b. I have an x to the first on the top with an x to the fourth on the bottom, so that x to the first on the top will be gone, and that means I only have 3 left on the bottom. And then since I have y on the top and bottom, those just cancel out completely because they're both y to the first. So I have 7a squared on the top, and then 15b squared x cubed on the bottom. And that would be my most simplified answer. So your answer should, again, have a simplified fraction for the coefficients, and each variable should only appear one time. If you have the same variable on the top and the bottom, you can simplify that. So let's look at B. B is division. So here what you have to do first is rewrite it. So you keep the first fraction the same. So before you start simplifying, make sure you rewrite it. Change the division to a product, so it's multiplication, and you flip the second fraction. So now I have 7a squared b squared on the top and 24m cubed on the bottom. Now that I've changed it to a product, I can do exactly what I did up above. So I'm going to look at the 16 and 24. I can divide those both by 8. So the 16 is 2, the 24 is 3. The 21 and 7, I can divide both by 7. So 7 becomes a 1, 21 becomes a 3. So if I multiply across, 2 times 1 is 2. All my variables are different. I'm going to put them in alphabetical order. So a squared, b squared, m, t squared. And then on the bottom, 3 times 3 is 9. And again, my variables are all different. If your variables, if you had any of the same variable, like say instead of this being an m cubed, it was an a cubed. So remember, when I multiply those together, then you add their exponents. So if your variables are the same, you add their exponents. Then when I get here, 2 over 9 is simplified, but I can simplify the variables. So I have a squared on top, a to the fourth on the bottom. That means the a squared is going to be gone from the top, and if I take 2 away from the 4 on the bottom, I have an a squared. B squared on top, b cubed on the bottom. The b squared on top is gone. I have a b to the first left in the bottom. I have m to the first on the top and m cubed on the bottom. So the m on the top is gone, and I have m squared left on the bottom. And then I only have the t squared on the top. So I have 2t squared on the top, 9a squared b to the first, and then m squared on the bottom. And that would be final. Okay, so actually, because there's only that one left, why don't you go ahead, again, work on this one. If you need to pause it so that you have enough time to work through it before I show the answer, do so, but work through that one, and I will also, and then you can check your answer. All right, if you need to pause it, pause it. I'll show the answer here. So this is what you should have as a final answer. You can, freeze this up here if you need to. But one thing I had described it above, it actually happened here. When I multiply the x to the fourth by the x to the first here, that becomes x to the fifth. So if you do have that same variable, make sure you add the exponents.